yeah. I mean, yeah.
Okay, thank you.
Shall we get started, Anna?
Yeah, I think so. Yeah.
Okay, and I'll introduce the session. I hope you all enjoyed the very short break. My name is Bert Wouters. First of all, I'd like to welcome you to our session, also on behalf of my co-chairs, of course, Anna Haug, Sushila Tusumidi, and Lawrence Gray. So in the previous session today and yesterday, we looked at the large ice sheets of Greenland and Antarctica. In our session, we'll focus on the smaller bits and pieces of the ice spheres, so ice caps, mountain glaciers, and icebergs, and ice shelves, of course. There has been a slight change in the program, so unfortunately, CK Shun can't make it today. So we will use the fourth slot of our session for additional questions to the presenters and maybe also a short break. I think we deserve that. This also means that we can be a bit more flexible on the timing of the first few presentations, but nevertheless, we'll give you time 1 minute before the end of the allocated time, of course. I've also been asked to remind the audience to submit questions through the WebEx chat function, but I think you already know that now. So with that, I think we can start, and we'll start with a keynote by Helen Frigger, who will discuss the advances in understanding Antarctic ice shelves using satellite altimetry. Helen, the WebEx floor is all yours.
Great, thank you. Just going to get my notes up here. Sorry, I'm a bit behind the 8 ball today. It's 2 a.m. local time, not usually up at this hour. Okay, but it's great to be here and great to see everyone. And there's Cecile, he's in the same time zone, so we're both in the middle of the night. So first of all, thank you to the conveners for having me here today, tonight, whatever it is. And thank you to the organizers for my lovely CryoSat polo shirt. I don't know if you can see it, but I did put it on specially because this was a lovely gift to get during lockdown. As you all know, this conference was supposed to be in Italy, and I had tickets booked and everything. It was very, very sad, but this is better than nothing, and I'm looking forward to when we can see each other all again. Okay, so yeah, so my talk is about what we've learned about the Antarctic ice shelves using satellite altimetry, and it covers a lot of ground, but it's 2 a.m., so it probably will be a little bit superficial, hitting the highlights, and I'm not going to go into too much technical detail on anything, but we can definitely answer any questions that you have later when we're awake in our time zone. So send us emails and things like that. So this is a very collaborative effort, of course, and many wonderful people have been involved in this work, and I've tried to highlight many different ice shelf research projects that have happened with altimetry. So I'm going to start out by going all the way back to right before ERS-1 was launched. And actually, when I prepared this slide, I didn't know that Chris Rapley was in the audience, and I'm delighted that he is. So this takes us all the way back to the 90s. Can you guys still hear me?
No, I can't see the slides though. So could you share again?
No. Okay. Thanks, Sushil. How's that?
Still in like, oh, there we go. Yeah.
Yeah. Okay, so we're going to go back to the 1990s. So I was an undergraduate at UCL, and I was fortunate enough to be taught a class in my final year by Chris Rapley. And Chris introduced me to the excitement of satellite remote sensing. And to someone who was doing maths and physics at UCL, that was like the most amazing thing I'd ever heard of. And actually, it still is, even 30 years later. So thank you, Chris, for introducing me to this exciting world. It was right before ERS-1 was launched. So what a time to get involved in ice sheet science. And Chris introduced me to Seymour Laxton, who at the time was a postdoc working with Chris. And Seymour actually became my supervisor for my first project on the ice sheets. So many people in the audience will recognize this, Homebrew St. Mary, where it all started, MSSL. But let's just have a think now about what we were all thinking about the ice sheets back then. So I've decided to base this around a storyline that was recently posted on Twitter. I'm not usually one to sort of blast social media in my talks, but I was quite proud of this one. I nearly got 1,000 likes for the first time ever, and maybe it will eventually by the end of the week. So just in the 1990s, we thought about the ice sheets as obviously very large, but slowly changing freshwater reservoirs. And we knew that they had grown and shrunk over long, long time periods. But that was what we thought about the ice sheets, that they changed on long time scales. And so this is a figure from the IPCC that shows this, and the ice sheets are sort of mainly in this long time scale mode here. And this is reflected in the IPCC reports, and the first and second assessment reports concluded that basically the ice sheets are changing really slowly and we didn't really need to worry about them. And this is like people like me had this report on my desk when I was going into my PhD. So the ice sheets, they matter a bit, but not that much. That's what we thought. And so around about that time, I actually headed off to Hobart to do my PhD, and Jonathan, who was also a postdoc at the time with Seymour, he had made his first digital elevation model of Antarctica using ERS-1. So this is a really nice way to, it's a snapshot of the ice sheet, and really, really important product for ice sheet modeling, and many other things were done with this product. And so it gave us a snapshot of the height at this time. And here is me. I kind of thought I'd throw a slide of me in there. We were actually validating GPS validating altimetry using GPS on the Amory ice shelf, because we now had some data of 3 or 4 years of data collected over the ice shelf, and we wanted to know how accurate the data were over the ice shelves. So Jonathan and Jenny, in sort of towards the end of the 2000s, they used ERS-1 data to create a snapshot of ice shelf thickness, which was really useful, again, to show us, you know, how thick the ice is all around the floating parts of Antarctica. So the thickest parts sort of down near the southern part of the Amory ice shelf, on the order of about 2,000 meters or so. I use that map. I use a similar product, and combined with some airborne data to infer how much marine ice was underneath Amory ice shelf. Turned out that was a very significant amount, about 200 meters or so along this flow line. And this kicked off a whole research program with the Australian Antarctic Division. And they subsequently did 3 drilling seasons through the ice shelf to try and get the sub-ocean conditions, all from this map that came from radar altimetry primarily. Okay, so this is kind of coming into the early 2000s, where things started to change in our thinking about how the ice sheets work. We had this big wake-up call. Many of you will remember this very, very clearly. This is Ted's paper and his imagery that he put together showing the collapse of the Larsen B ice shelf. And this was over a period of 6 weeks. The ice shelf went from this, where the ice front is here, to this, where the ice shelf is just smattered into smithereens. And we were suddenly like, wow, okay, this is a really big deal. We've now got large changes happening on short time periods. And actually the thread mentions Greenland too, because my colleague Fiamma Stranio at Scripps helped write the op-ed from which this Twitter thread is all about, which you will hear about at the end. So we were starting to see these big changes happening in both ice sheets, and it really made us think, wow, okay, maybe we can't just be a bit complacent here. We do need to really understand what's going on. So it wasn't just the collapse of the ice shelf, of the ice, that caused alarm. As we all know, ice shelves displace the weight in water, and so they're already floating. So you're not going to get any sea level rise from that, but it's the ice behind that we're worried about, because as you remove the ice shelf, you remove the buttressing force, and the ice grounded behind it will flow faster into the ocean. So this is an architectural buttress, very similar thing. It's holding back the grounded ice. You remove that or you thin the ice shelf or remove the ice shelf, that will actually weaken the buttressing force, and the grounded ice will flow faster into the ocean, and that will give sea level rise. So that's turned out that was something we really needed to be thinking about. And this is, again, very early on in the days of our understanding of how ice sheets worked. So let's just have a think about how you grow or shrink an ice shelf. What processes are responsible for that? Well, you add mass to the ice sheet using just by snowfall and flow across the grounding line. And then ice is redistributed at the base by a process called refreezing, and that's the marine ice that I actually mentioned a little bit ago. And then ice is lost again through mainly two processes, because the surface melt is a very small component in Antarctica, basal melting and iceberg carving, which integrated all around Antarctica account for roughly half and half. So these are the processes that we needed to understand and needed to monitor to try and figure out where the ice shelves are changing and how. Okay. I don't usually use notes, but I don't usually talk at 2 a.m. either. So sorry about this. Wake up my phone. Okay. So this is around about the time where we had enough data from ERS-1 that we could start to look at trends. And these are obviously very short-term trends because we only had a few years of data. But I think this is one of the first maps from Duncan Wingham looking at height changes over the grounded ice. And this is showing, and this is another map from Jay's Wally, which also includes the ice shelves. And this color scale is a little bit tricky, and actually this one is not that easy to determine either. But what we're essentially seeing here is that there are large changes in height over in the west of Antarctica, over in the Amundsen and the Bellingshausen seas. So what this was showing was floating ice was thinning and possibly breaking off in some cases, and the ice behind it was flowing faster into the ocean. So Andy, who I think is in the audience, I've been WhatsApping him and telling him I was awake. I think he was worried that I might not make it. So Andy had looked at the at ERS over the floating part of the Larsen ice shelf, the Larsen sea ice shelf, showing that had been thinning there as well. So this is the first kind of changes in thickness over the ice shelves, over the floating parts of the ice sheet. Okay, so we were sort of building up this picture where we now see we've got changes going on all around the ice sheet, especially in the west and on the peninsula, and the altimetry is showing that the ice is getting thinner in these places. And so we at Scripps, I mean, I was kind of just starting out my postdoc, and it was kind of almost by accident. I mean, I found myself at Scripps, and it's obviously an interdisciplinary research center, and we have a lot of oceanographers, a lot of solid earth geophysicists, and also atmospheric scientists. And it seemed like studying ice shelves was a really good thing to do there, because there's a lot of people that have that sort of broad knowledge. One of the things about ice shelves that makes it tricky for altimetry is the fact they go up and down with the tides. I love this, always have loved this little movie that Laurie Padman put together many years ago, maybe even 20 years ago. So I actually teamed up with Laurie, who was just up the coast at ESR, and we started looking at height changes over ice shelves. And one of the things that we did, and this came on along a little bit later, but it's just to show you what you can do with this tidal signal, is you can actually exploit that to show you the flexure, or the limit of flexure, which is the grounding line, which is a very important parameter for monitoring ice sheets. And other people will know about INSAR techniques to do something similar. Okay, so we were knowing that the changes are occurring in the west coast, the Bellingshausen and Amundsen Sea, and also we knew there were changes going on over here as well from atmospheric driven. Basically, wasn't really that surprising. We did know that the oceans had absorbed about 90% of the extra heat accumulated, and so this transport of heat flux to the ice shelves probably wasn't that surprising in the end, but we were putting it all together and the puzzle was coming together. So this map here was quite illuminating, where we plotted the the temperatures off the continental shelf on top of a map this was from Hamish Pritchard, who actually came to Scripps to do this work with me, and we published it in 2012, but the data were collected in the 2000s. So this was Icesat now, so this is a laser altimeter, and this is just looking at trends over the Icesat mission. So 5 or 6 years changes in height just over the ice shelves. And so where the height changes are the largest, which is the red color, it's close to where the warm water is. So this is a spillhouse projection of Antarctica, and you can see that Antarctica is very much in the middle of the oceans. If you look at it this way, it's surrounded by ocean, and you get a lot of potential for heat flux to be delivered under the ice shelves. And so it was becoming clear that this is what was happening. Okay, so it wasn't really that surprising it was happening, but I think the rate at which it was happening was becoming surprising to people. This was no longer this case that Antarctica is this sort of sleepy ice sheet that doesn't do much. It's actually starting to change really quickly, and that hadn't been predicted by models, which was a problem, to the point that the IPCC, throughout this challenge in their 4th report to the whole community, basically saying, you guys don't really know what's happening with the ice sheet. We don't know enough about the processes that are going on, and you need to go away and figure it out for the next report, basically, because we're not going to include it in this one. And so that sort of set people off to go away and do some modeling and collect data, and a whole lot of very, very incredible modeling efforts have been led as a result of that. And I think Sophie is here. So yeah, this is one sort of branch of what happened, but what we focused on in our group was collecting more data over the ice shelves. And so the time series is now becoming a key thing. We need to understand the processes, right? Like not just the trends and short sort of DH over a short time. We actually want to know how we care about the wiggles. We care about how that variation is happening and the patterns in that. So Fernando Paulo, most of you probably will know this paper from 2015. And what Fernando did was stitched together 3 ESA missions, radar altimetry from ERS-1 all the way to NBSat to give 18 years of change. And so thickness changes over the ice shelves here. And these circles are actually representing how large the changes are. So there's some very striking changes going on over here in the Amundsen Sea. And so with the time series, you could actually determine that there was accelerating volume loss, especially coming from West Antarctica, and overall average together, we were seeing increased volume loss from the ice shelves. And the other thing that Fernando did was look at specific processes, and this is again in the Amundsen Sea. And in this case, Fernando was able to, he took out the trend and then looked at what was left behind and analyzed that, and found out that there was a very strong signature of ENSO on top of the trend. And this is, I thought I'd show this because it's kind of interesting. Not many people know this, but well, if you're the reviewer of this paper, you will know this. But when we first submitted the paper, it was only up until the end of NBSat, up until 2012. And we submitted it around about here, which is during a very strong El Nino event. And the reviewer asked us if we could include it. Well, long story short, we actually decided, actually it was at the last CryoSat meeting in Banff that we made this decision to include CryoSat in the analysis to see if we could pick up the other El Nino. So I'll reveal to you now what CryoSat gave us for this. So there we go. Here's the other El Nino, and it was very, very lucky that we did it because it was a very, very nice El Nino, and it really gave us an extra sort of solidified the result. I'm really glad that we did that extra work. So thank you, reviewer, too, whoever you are. So yeah, this was really now showing us that we can use these time series to understand processes and really try and unravel the signal to try and determine which processes, atmospheric, oceanic, are dominating on what timescales, and how is the ice shelf changing in response to that. Okay, and then the other thing that we did looking at processes was teamed up with Hilmar Gudmundsson and looked to see what was the response of the grounded ice to those changes in ice shelf thickness. And in this case now, the circles are proportional to the change in speed in the grounded ice. And so inputting in those height changes that I showed you from Fernando's data, what does it look like? And so this is what we found. So lo and behold, the largest speed up is happening in the Amundsen Sea, which is really a reinforcement or just confirming this whole concept of ice shelf buttressing, right? Like you thin the ice shelf and the ice flows faster, the grounded ice flows faster. So this was a nice sort of confirmation of that. So where were we in our thinking, like this whole Twitter thread that I'm trying to use to tie together this talk? We knew there were processes going on the ice sheet. We didn't know if we knew about them all yet. There was still some gaps in our understanding. But what we did know was that sea level would continue to rise in the future, and probably faster, especially as that contribution from Antarctica was kicking in, and possibly a contribution from East Antarctica, which is a very large reservoir of water. This here is I love this plot because it really brings it out to you. Like the darker the blue here, the more ice you've got. So this is 12 meters of sea level potential in this basin, 9.6. Yeah, most of it is in East Antarctica. So this is underscoring why we need to keep monitoring the ice sheets and use altimetry to figure out where and how they're changing and when. Okay. Along came Icesat 2. This was 2008 launch, the follow-on mission for Icesat. And what we did with this mission on the Icesat 2 science team, and Ben Smith is the lead of the land ice part of that team. We differenced the data from Icesat 2 to Icesat over the same time period over the whole ice sheet, including the ice shelves. And this actually hasn't been done that often. Most times we split up the grounded ice and the floating ice for analyses, but this was a opportunity to do that and see whether we could really see changes in grounded ice in response to changes in the ice shelves, and we did. So this was actually showing a plot that Sushil made going all around the grounding line of Antarctica, showing the mass changes and where they were the largest. So the largest mass changes over here in the Amundsen Sea and the Bellingshausen Sea. I'm using the plot from the New York Times rather than from the science article, because I just thought the New York Times did such a lovely job of illustrating these changes. And there's some other very nice things in here that the altimetry picked up, like the slowdown of ice stream, CAM ice stream. Okay, how am I doing for time? Okay, 3 minutes. Okay, so this is showing just the difference between, we all know that they're, mixing radar altimetry and laser altimetry. We all know that's, there's an issue there because of the radar penetration bias, and Icesat doesn't have that problem because Icesat is top of snow reflection. So Sushil did this for his thesis, actually, which he just defended a couple of weeks ago. And so on the left here is Icesat 2 minus Icesat, the map I just showed you, but just in slightly different scale. And on the right is CryoSat minus EnviSat for the same time period. And so, you could look at this. It's not probably very easy to see just on the screen, but you could look at these slides in more detail later. But you can definitely see some areas that we could focus on to try and understand the differences there between the two instruments. But like I said, it's 2:30 a.m. and I'm not going to go into those details too much. The other thing that Sushil did, and this was an important step, was now we have a long time series, and extending it now with CryoSat, the high spatial resolution measurements over the ice shelves. He was able to turn that into a time varying basal melt rate. Now, this is a lot of work went into this, and I'm definitely diminishing all of the work that he did by just showing like one slide. But this is a very nice end result derived from the CryoSat data. The initial big sort of contribution was melt rates at high spatial resolution for the CryoSat period, so 2010 to 2018, but then also bringing back going all the way back to the older radar altimetry to get time varying melt rates as well. So there were two data sets that were provided with this paper, and these are going to be really useful for inputting into the models that we're trying to ultimately use to include into the IPCC. So what's the freshwater flux from the ice sheet? Well, We have a pretty good idea now because of the altimetry data. And just to give you an idea of how much we've improved compared to what we were using before, these are the results that we had before, the Icesat period. These are the measurements that we used before. And so this is showing a time varying, very strong temporal signal here in the melt rates. So let's have a look at the Amundsen Sea. This is showing the beautiful sort of high resolution pictures that you can get from CryoSat. And so look at Getz and Dotson here. And then Dotson has this lovely melt channel, which was also shown to us by Noel Gormelin, who I believe might be in the audience. Beautiful paper here. And this was really, really nice, showing that you get channelized melting under ice shelves. So this is now helping us learn where the ice shelves are being eroded from the bottom the most. And CryoSat's really giving us a picture into that. And so, yeah, these are the this is large temporal variability in the melt rates in the Amundsen Sea. So they're varying quite a bit here. If you just use one constant melt rate for one period, then you get quite a different result in your model from using this time varying. So yeah, just moving on to the sort of more high resolution altimetry and what you can get from this. I mainly did this for Icesat 2, but I added CryoSat as well. Because obviously this is a CryoSat meeting, and CryoSat can actually get to a lot of these processes as well. So there's many mass processes that we need to understand in the ice sheets that we can get. Okay, that's my time. That we can capture with high resolution altimetry. So Icesat 2 and CryoSat 2, these are the first altimeter missions that are capable of resolving processes at these spatial scales. And so basal melting, carving, surface melting, accumulation for Icesat 2 and refreezing for both. We also grounding zone was the other one, but I mentioned that one earlier. So the point is we're gathering more and more data on the ice sheets using all the tools and all these new high resolution satellites, and our observational record is getting longer. Our understanding is improving. And as our understanding is improving, hopefully our models are going to get better too, which puts us in a better place to predict the future. So just to give you some examples and some highlights of some of the work that we're getting out of the Icesat 2 instrument, this was in the Smith et al. Paper showing the improvement in resolution over ice shelf rifts. This is Icesat and this is Icesat 2. To be fair, this rift actually did change during that time period, so it's not just there's more going on here than just improved resolution, but you can really see the detail that Icesat 2 captures. We also looked at a carving event in great detail from Emery Ice Shelf, and this gave us some really nice data to actually look at active rifting right before the carving event, and then changes in the ice mass as the iceberg carved away. This is with Catherine Walker. Okay. Oops, I just went back 2 slides. And then my student Maya Becker has been doing some really nice work looking at the front of ice shelves. I'm looking at this feature which is related to small scale carving. And it also can tell us information about the oceanic and glaciological conditions right at the ice front as well. And this paper actually just came out in GRL a couple of days ago. Again, flashback to the 1990s, we used radar altimetry back then to look where the return was specular over the waveform was specular, and turned out that was because there was surface melt on the ice sheet, well, on the ice shelf, and the surface melt streams were very wide, so they made they caused a specular return in the radar altimeter, and the specular returns lined up along this trough. Long story short, we revisited the same lakes or similar lakes with Icesat 2, and Icesat 2, because it's 532 nanometers, is able to penetrate through the water. So the photons bounce from the top of the water surface and from the bottom as well. And this is going to be really nice for helping us to improve the image-based techniques for retrieving melt depths on over ice sheets, because the Icesat 2 data, even though there aren't as many of them spatially, they're actually more accurate than the imagery, so we can use them to train to train the models. And yeah, and Bert was involved in this study. So thank you, Bert. And then this is final sort of thing I want to show. This paper has actually just come out as well. It's a doe line on Emery Ice Shelf. It's a surface melt lake, which was covered in ice before drainage, and it drained during the winter of 2019. And we were able to capture it with Icesat-2 data. And what that did was the water went all the way through the ice shelf and drained, and the doe line collapsed. And as a result, the whole ice shelf rebounded because the load of water had gone away to the ocean. And so there was a flexural rebound here, which we could use to model and estimate the volume of the water. So this is quite a significant event that was captured really nicely in Icesat-2 and also in Worldview. All right, so just to wrap up, and this is sort of the end of this Twitter thread that I was trying to highlight here. We need to think about the future, of course. We've been in the glory days of altimetry. I mean, my sort of 30-year career in altimetry has really spanned some of the best. We've definitely had some highlights, but we need to make sure that keeps going, and that it keeps better and better. We need to keep our international collaborations going so that we can strategically place missions up there to monitor the ice sheets, and so that we don't have a gap. These measurements are so key to delivering more accurate predictions. We just need to be able to see what's going on the ice sheets. Okay, and international collaboration, very, very key. Okay, so this was a huge team effort, and I stole Andy's tweet, which was his team sport. I really like this one, and then I sort of made another one over here too. These are all the people that featured in this talk. So many incredible people involved in this work across both ice sheets all around the world. Can't mention them all individually. Definitely a community effort. We have to work together. We shouldn't be working alone and trying to sort of run to the finish line. No one's going to get there first. And that's the point. Large, collaborative, inclusive teams get important work done. And in case you're wondering what on earth that Twitter thread was all about, well, this is it. So Walid Abdelati wrote an op-ed, and I don't even know what op-ed stands for, opinion something, education, in The Hill, which is apparently a very influential publication in Washington, D.C. And Walid's was all about what's NASA's role in addressing climate change. And then Fiamma Stranio of Scripps and myself wrote one about the ice sheets and what we've learned and how the modeling has sort of gone hand in hand with our knowledge and the measurements. And so if you want to know more, you can go to find that on Twitter. And the reason why I try to make a point of doing these sort of conversation articles and op-ed articles, and I think we should all be doing this, is it comes back to this quote. And Chris Rapley he would know where this came from because it's a session that he and I were part of at AGU a couple of years ago. So Jane Lubchenco, who's now involved in the Biden a team to address sort of the environmental issues and climate issues, and we're so lucky that she's there. Scientists today are privileged to be able to indulge their passions for science and simultaneously to provide something useful to society. With these privileges, of course, comes serious responsibility, i.e. we need to communicate what we've learned and tell the public, because it's super important, and they're not going to know from our papers because they're not going to understand those. So, okay, thank you very much. I might go back to sleep now.
Thanks so much, Helen. That's a fantastic talk, and I think we can all agree with Lawrence's comment in the chat that this was the best 2 a.m. talk ever. So take that and tweet it. We've got a few questions and we are running over, so we might not be able to get through all of them, but I think I'll start with Andy's 3, which are the main ones that I can see in the chat, as they're so relevant to the decade of measurements we have from CryoSat. So first question is, do NASA have any plans for an altimeter mission post Icesat-2?
Is that from Andy?
It's from Andy Shepherd, yes.
At 2:40 a.m.
Yeah.
Okay, so actually, I showed on there in my future mission slide, there was a copy of this big fat book called the Decadal Survey, which I actually was on the steering committee for. And in that, we put forward some variables that need to be monitored through the Explorer class of missions. And one of those was ice elevation. And Yes, basically there will be some mission launch and it will be competed fairly soon. I don't know the exact timeline, but this is something that is in the works, and I don't know if there's anybody from NASA on here that can speak more. I mean, it is only 5:41 a.m. on the East Coast, so maybe they're up.
That's great. It would be great if we can have a NASA mission to complement the ESA ones. The next question is about the status of Operation Icebridge, again from Andy. Is there a chance it could be restarted now that NASA have had a budget uplift?
I am not aware of any reinstigation of Operation Icebridge, but I don't know for sure. My understanding was that the budget for NASA was going to be for the Explorer missions, but I could be wrong.
And final question in this quick fire round is on a more technical one, again from Andy. I've seen examples of supraglacial lake depths from Icesat 2, and you showed this in one of your final slides. Is this penetration restricted to water, or do you think the laser could penetrate into fern also?
Yeah, interesting question. Uta has been talking about that, possibly that she is able to see penetration into the fern. We don't know yet. Nobody has really unequivocally shown it. So yeah, it's a working progress. Maybe somebody else on this call has seen it. I mean, the data are all out there, right? Anybody can use them. So
that's fantastic. Thanks so much, Helen. Awesome presentation, especially at 2 a.m. and a mini Viva at the end of that as well. So thank you so much for participating.
Yeah.
And we'll move over to the next speaker now. So up next is Anne Brockman-Fogelman from the University of Leeds. She's a PhD researcher in Andy Shepherd's group, and she's here today to present on combining Sentinel-1 and CryoSat 2 measurements to track icebergs. So Anne, how are you going? Have you got the technology working, and are you able to share your screen?
I will try. Thank you for the introduction. Can you see my screen?
We can see the PowerPoint, and yes, now it's in proper presentation mode, so you're good to go. We'll give you a 1-minute warning, but you've got your full time allocation.
Perfect. Thank you very much. Yeah, good morning, everyone. I'm Anne Brockman-Fogelman, and as Anna said, I'm a PhD student at the University of Leeds, working on the remote sensing of icebergs. And today I'm going to present some work on the combination of CryoSat 2 measurements with satellite altimetry to track tabular icebergs. And yeah, first of all, why do we care about icebergs? As Helen already said, iceberg carving accounts for about half of all ice loss from Antarctica. And therefore, there's simply a vast amount of ice floating around in the Southern Ocean in the form of icebergs. And all these icebergs affect and interact with the Antarctic environment in a range of processes, as you can see on the graphic on the right. So when icebergs release cold, fresh meltwater, this influences the local ocean circulation. It also facilitates sea ice growth. But icebergs also carry debris containing terrigenous nutrients. And when these are released, that fosters the biological production around icebergs. And this in turn also attracts seabirds and larger animals. And yeah, therefore, to quantify the amount of melting and where this happens, we need to monitor the iceberg volume change along its trajectory. And in this talk, I'm going to look at one specific iceberg called B30. And we want to monitor the area change, the freeboard change, the thickness change, and finally the volume change of this iceberg. And we also investigate to which extent this monitoring can be automated. And then finally, we propose a way to model snow accumulation on top of the iceberg and assess the impact of this. So this specific B30 iceberg carved from the Thwaites ice shelf in 2012, and then followed the coastal current along Mary Bird Land and started drifting north in 2017 and eventually disintegrated in 2019. And on the left, you can see a Sentinel-1 image of the iceberg. And initially, the iceberg was 59 kilometers long and 315 meters thick. So it's really large, a large tabular iceberg. And you can also see from the picture that the surface is very crevassed, which is typical for the Thwaites ice shelf. Then, first of all, we delineate the iceberg's area in satellite imagery, and we use both optical imagery from MODIS as well as synthetic aperture radar imagery from Sentinel-1. And on the left, you can see a sample outline. And then on the right, you can see all the outlines that we use for our area calculations and how the shape develops over time. So in the beginning, the iceberg is losing smaller pieces around its edges, but the shape stays relatively the same. And then towards the end, larger pieces are lost. And this is also when the iceberg has reached the open ocean, and therefore it's exposed to waves and also to warmer ocean and air temperatures, which is causing the larger breakups. Now, when we plot iceberg area over time, we can see that the iceberg had an initial area of 1,500 square kilometers. And after 6.5 years, this has reduced to 426 square kilometers, which is a reduction by 72%. And we also observe that the loss is quite linear up to 2018, where the iceberg then started to lose bigger pieces more rapidly, as I said on the previous slide. And yeah, now since deriving iceberg area from these manual delineations is quite tedious and requires a lot of manual interaction, we also looked into two different approaches that can be automated, and we compare them to the imagery derived iceberg outlines. Yeah, and the first idea was to use semi-axes, which are provided by the National Ice Center on an operational basis, and to assume that the iceberg has an elliptical shape, and that's the blue line in the plot here. Yeah, and although we find very high correlation coefficients, both the area and area change are overestimated throughout. And the main problem here is, first of all, that we have to make this assumption of an elliptical shape, but also that the semi-axis estimates are updated infrequently and they are always rounded to nautical miles. Then our second idea was to use the arc length from CryoSat overpasses and to assume that the iceberg has a circular shape. So in this sample image, you can see one overpass from CryoSat, and we basically just take this arc length and assume the iceberg is a circle, which obviously is an even bigger assumption. But this would be one approach that could be automated. And yeah, in the time series, you can see that there's quite a bit of variation from these arc lengths, and that's because CryoSat samples the edges more often than the long axis. Yeah, and therefore we also find an underestimation of both the area and the area trend, but still actually quite good correlation coefficients of 90%. And to conclude, we can say that there are alternative approaches to estimate iceberg area or trends in iceberg area, but by far the most accurate is still the satellite imagery and clicking these manual outlines. And now to get a full three-dimensional view of the iceberg, we also need to measure its thickness, or first of all, the freeboard of the iceberg. And we do this using the CryoSat measurements processed from level 1B. And first, we start by looking at the initial iceberg freeboard before the iceberg actually calved. So here it's still attached to the Thwaites ice shelf. And by using satellite imagery before and after calving, we derived the part where the iceberg comes from. And that's the black polygon in the image. Then we collected all measurements over this area for almost 5 months before the iceberg calved and gridded them as shown in the second plot. And this gives us a map of the initial iceberg freeboard, which is 49 meters on average. And this is important because we then want to compare later overpasses over the floating iceberg to the same grid cell of the initial map. And here you can see 12 CryoSat overpasses together with near coincident satellite imagery. And we transformed the initial polygon outline in red to match the imagery on each of these occasions. And yeah, this then allows us to collocate each of these CryoSat overflights with the initial freeboard map. And here in the top 12 plots, you can see the same 12 CryoSat overpasses that are now collocated and different to the gridded initial map. And this shows that the iceberg is melting quite uniformly across space. And then when we average each of these overpasses, we can also plot freeboard change over time. That's the blue diamonds in the time series. But again, we wanted to test a different approach that does not require this, again, manual interaction of collocating the tracks. So we also tried to just use the average of each overpass and difference it to the average initial height. And that's basically all the other blue measurements filled in the time series here, which gives us denser sampling. And in the small scatter plot here, we compare our non-collocated tracks to the collocated tracks, and we actually find good agreement. And also from the time series, you can see that the measurements agree quite well, but there's more variation from the non-collocated tracks. And yeah, we can also say that the collocation does improve the accuracy, but for this iceberg, it's only a slight effect. And yeah, combining both the non-collocated and the collocated tracks, we find a total freeboard reduction by 9.2 meters after 6.5 years. But yeah, in reality, what we're really interested in is not only the freeboard, but actually the total iceberg thickness. And therefore, we want to convert our freeboard to thickness, and we assume the iceberg is floating in hydrostatic equilibrium. But then we also need to know the densities of seawater and the density of the iceberg. And for the ice density, we fitted two parameters to the depth of critical density levels of the Thwaites ice shelf, where the iceberg calved from, to get this ice density profile as plotted here. And then as the iceberg thins, actually the densest ice is melted from the bottom. So we basically crop this density profile and calculate new averages as the iceberg thins. Then another thing to consider is the snow accumulation on top of the iceberg surface. And for this, we use ERA5 reanalysis data of snowfall, snow melt, and snow evaporation. And we find that the iceberg accumulates 4.6 meters of snow water equivalent during its drift, which is quite a lot. And yeah, with evolving snow densities that I will explain next, this even converts to 7.2 meters of snow depth after 6.5 years. And in the equation, we also added an extra term for the snow layer. Yeah, and then for snow density, this increases as a function of wind speed, air temperature, and snow depth. So we model the snow density as a function of these variables, and all of these are again taken from ERA5 reanalysis data. And this then allows us to model this compaction of the snow layer, as you can see plotted here. And after 6.5 years, the snow layer has a density of just over 600 kilograms per cubic meter. Yeah, and based on all of these assumptions, or when we find this really thick snow layer, and we also find that the snow layer evolves and compacts so much over time. And then what I also plotted here is the degree hours. So based on air temperature, we see that there's positive air temperatures every summer, and this will lead to surface thawing. And therefore, we assume that CryoSat does not penetrate this really thick and compact snow layer. Yeah, and then with these assumptions and models, we can finally derive the iceberg thickness change shown here. And we find a decrease by 117 meters after 6.5 years. And in the plot, you can also see the impact of the snow layer from the dotted line. So if we wouldn't account for the snow, this would make a 23% difference. And therefore, we conclude that at least for icebergs that survive over several years, it's really important to include the snow accumulation in the calculations. And yeah, another thing you can see from this time series is that the iceberg does not only, the thickness does not only decrease, but there's also a short time period where it actually increases. And we thought about potential explanations for this. And we first of all looked at where the iceberg is during this time. And it's floating really close to the Gat's ice shelf and really close to the coast during this time. And therefore, we have a range of possible explanations what could have caused a thickness increase. And the first one is marine ice formation. So other studies have found increased marine ice formation along the western sides of ice shelves. And as the iceberg is really close to the western side of Gat's ice shelf at this time, this seems likely. Another explanation would be additional snow accumulation on top of what we've modeled from the ERA 5 data. So this could either be local snowfall, or it could be snow being blown off the continent through strong katabatic winds. And again, this seems likely as the iceberg is so close to the coast. And the last option for a real thickness increase is, you can see in the animation that the iceberg collided with the ice shelf at least once. And this could have led to a slight compression and therefore also a thickness increase in some parts. And yeah, apart from these causes for a real physical thickness increase, it could also be that our measurements just show higher freeboards. And this could either be because the iceberg's grounding for a short time and therefore no longer in hydrostatic equilibrium. Or it could be that there's a shift in the scattering horizon for CryoSat, because we also find high air temperatures during the turn of the year. And that, yeah, this could have shifted the CryoSat scattering horizon. And overall, we can't really decide what actually caused the thickness increase, but probably it was a combination of several effects. Yeah, and then finally, we can combine our time series of thickness change and area change to derive the total volume loss, which was 378 cubic kilometers overall. And this corresponds to 80% of the initial iceberg volume. And converted to mass, this is 325 gigatons. And then if we want to know the freshwater input, we have to distinguish between melting and fragmentation. So roughly 1/3 of the volume loss is caused by basal melting and 2/3 are caused by fragmentation. And while basal melting can be used as a lower bound estimate of the immediate freshwater flux, the fragmentation depends on the size of the pieces which are lost. So smaller pieces and side melting will also add to the direct freshwater flux, but larger calving events of smaller icebergs can survive longer and travel further. Yeah, and just to sum this up again, we found a total area loss of 426 square kilometers of the B30 iceberg, a total thickness loss of 117 meters, and a total volume loss of 378 cubic kilometers over the study period. And then 69% were through fragmentation and 31% were through melting at the iceberg's base. Yeah, and as conclusion, we can say that, as I said in the beginning, iceberg melting is important because it influences the ocean circulation, the sea ice formation, and biological production. So our goal was to derive the total volume loss and the freshwater input from this iceberg. And yeah, that's what we've done. Concerning the possibility to automate our calculations, we found that satellite imagery offers the most accurate estimate of iceberg area, but arc lengths from CryoSat and especially the semi-axis provided by the National Ice Center can still capture the trend. And in terms of collocation of the CryoSat tracks with respect to the map of initial Iceberg Freeboard, we found that this improves the accuracy only slightly for this iceberg, but this might be different for icebergs with either more topography across the iceberg or with less crevasses within each grid cell. And then finally, we demonstrated that the inclusion of a snow layer is important when we calculate iceberg thickness, at least when the iceberg survives over several years. Thank you very much.
Thank you, Anna. Great presentation, and thank you for staying on time. I got 3 questions in the chat. The first one by Lawrence Gray, who's asking, can you link breakup to sea states?
Sorry again?
Can you link the breakup of the iceberg, I think, to the sea state?
Well, we found that at least larger pieces only break off when, or mainly break off when the iceberg is in open water. So we do think that waves can trigger a break-off, but yeah, I'm not sure if it really just happens in high sea state, or if the swell is enough, and if it happens immediately, or if the waves just propagate the cracks which are maybe already there, and then it breaks up slightly later.
Yeah,
we haven't looked into specific sea state data.
Another question by Albert. Have you used either SAR or SAR-in data for the whole period analysis, or a combination of both?
Yeah, that's an interesting question. So when I started, I used the level 2 product from ESA, and I found that there was some really strange signal, or you basically couldn't see a melting signal at all. And then what I found was that the SAR and the SAR-in data is not really comparable, because different biases are applied and different retrackers are applied. And therefore we went back to level 1B data and processed both the SAR and the SAR-in waveforms with a common threshold retracker, and basically processed them in the same way. And this then gave a coherent signal of melting. So we're using both, but from level 1B data.
Yeah, thank you. Another question related to the processing. How do you process the Sentinel-1 SAR images to delineate the iceberg area? For example, how do you reduce the salt and pepper noise? Perhaps you could do that on Google Earth Engine.
Yeah, I've been using the ESA-Snap software, so I haven't done much processing actually. I've just applied the precise orbit files, and I've multi-looked the images to reduce some speckle noise and did the radiometric correction, but that was everything. And then I just manually clicked the outline of the iceberg, and in some images I found that an automatic delineation even worked with using a simple MATLAB function, but that was only possible when there was no sea ice around and when the iceberg outline was really clear, and otherwise I had to do it manually.
Thanks. Another question about this puzzling brief period of thickening, which is of large magnitude, about 15 meters. There's a question by Peter Nino. Does anyone know what the biggest uplift in the reflection horizon could be due to a new melt horizon? Maybe that's a more general question to the entire audience.
Yeah, I can't say, but I don't think it was just a scattering horizon uplift. So my feeling is that it was, if anything, a combination of several effects, and yeah, not just the scattering horizon.
Yeah, there are a few other questions, but we need to move on. Maybe these can be discussed offline, or maybe during the poster session. We will now continue with the next keynote talk by Noël Gourmel on SWOT processing of CryoSat 2 for global monitoring of mountain glaciers and ice caps. Noël, can you share your screen? Yeah, you see your see the weather in Edinburgh at the moment. Well, we can't hear you yet, and yeah, now we see the presentation. I think no longer the weather. Ah, there's the weather. I think you need to switch.
Can you hear me? Yeah, can you hear me now?
We can hear you, but we still see the weather forecast.
Yeah. All right. I was just saying I'd rather be in Italy. So, okay. Good morning, everyone, and thanks very much for the invitation to present. So, what I will do is show some activities and work that we've been doing actually over the last decade, so pretty much from the start of after the launch of CryoSat. I was unlucky enough to be part of the teams for the preparation over the last 20 or 30 years. But this is essentially work done through two activities which lasted quite a bit, CryoTap and Mountain Glacier. And it's been done by quite a lot of different people. So a lot of students and postdoc at Edinburgh, people at Earthwave over the last few years. ESA-Sat, who have been in his efforts from the beginning. People at CPOM, NVO. And I'd just like also to recognize some people at ESA. So Mark, Diego, Stephen, Jerome, and Tom, especially because I guess a lot of what we present benefit from the work that they do within ESA and within the member state to get these missions and projects and various activity going. So a big thank you to them. So Glaciers, there is only one talk this week, and I guess it's a testament to the difficulty of doing glacier studies from radar altimetry, but glaciers are important. Glaciers are the first contributor from the cryosphere to sea level currently. They are also planned to be to remain the first contributor to sea level rise over the century, and they also provide very important freshwater resources for populations. In some places and in some years, they dominate the contribution to hydrology over precipitation. In some sectors, they are the only source of fresh water. So they are key, and I guess that's the difference when we think about what I should do. And despite this, there's actually no mission currently with a primary objective to monitor volume change of glaciers. And again, it's because it's quite a difficult thing to do. If you look at CryoSat, the primary objectives obviously are sea ice and ice sheet. And ice capping glaciers actually were mentioned as secondary objective, which if that was done in the 90s, that was quite a bold plan, and kudos to ESA as well for accepting this. I think the first estimates of global glacier mass change actually even came after CryoSat was launched. So that was a bold statement to make. Luckily, we had a recipe for it. So this is from Duncan's paper, which essentially addresses the issue of ice capping glaciers, talk about the difficulty related to surface slope, mention the fact that in that case, CryoSat with this unique interferometric design and SAR interferometer will basically act as a side-looking SAR imager, and the possibility of doing swath mode, so following the wavefront as it interacts with surface, and if those tests that were planned are successful, then to generate algorithm for operational environment. And this is actually what we've spent the last decade doing. So that was well done for writing this. So Mountain Glacier, that's really proceeding to the use of CryoSat as a side-looking SAR to some extent through the swath altimetry, and using the fact that because of the interferometers, we can very precisely pinpoint where the echo comes from as the wavefront interacts with the surface. If there is a sloping terrain, then the echo predominantly comes from one side of the nadir. Is very well distinguishable, and you can essentially measure height along a swath. and that's yeah, and that's essentially that was demonstrated before CryoSat launch from Aziras. So that was work that Bob Holly, Andy, Duncan, Veit, and Rob published in GL at the time. That was overall Fauna to this section. Then Lawrence, very shortly after the launch of CryoSat, demonstrated that this could be done with actual CryoSat data that was over the Devon ice cap. So there are several reasons why SWAS is useful. One of which is that increase, obviously, spatial coverage. So if you have a swath of a few kilometers wide rather than just a point of closest approach or POCA, then you increase the point density, which is always good. But what it does as well is because of the large footprint from CryoSat and the fact that you have topography, which is sometimes of similar length scale than the footprint, you get the effect that the point of closest approach is often aligning at topographic ridge, and therefore you have a sampling issue with POCA radar altimetry. So this is an example in Young Local. That's an ice cap in Iceland. You can see the topographic line here. There is essentially a topographic high here. And if you look at the distribution of the POCA, you can see that it really aligns with the ridge. And the lower elevation sectors where you have the outlet glaciers, this is the ice velocity where you can pick up the outlet glaciers, are not sampled. And obviously that's an issue because there is a strong link between topography and elevation change. And SWAS basically cover this. So you're basically improving dramatically the sampling of the topography. So you're getting measurements in high elevation and measurements at the low elevation where thinning is usually higher. And what you do as well is, I mean, that was kind of mentioned in a paper by Duncan as well, is that in many situations, the retracking actually fails. So either because the surface slope is too high or because you have very high roughness. So that's an example. That's in Glacier, tributary to Peterman Glacier in Greenland. That's one pass from CryoSat, and you can see that all of these records are defaulted to nadir, which means the retracking failed because of the waveform wasn't clean enough, didn't have a proper leading edge. Applying SWAS, you can retrieve elevation for these particular waveforms and increase the set of observations from that. So we've quickly done some work on this, and we started by picking a relatively easy spot, which also had some validation data. Quite a lot of in situ measurements have been done there in Iceland. So that was done by Luca during his PhD. I believe that was the first, actually, in 2016, the first image of the thinning of ice caps in Iceland. That wasn't done before. I think Icesat, there was quite a lot of clouds, and also the coverage is not as good. Somehow there was no dam differencing. So that was the first time we had an actual idea of what the change in thickness in Iceland looked like. You're picking nicely the thinning at the margin. You also see local subsidence, that's Bardabunga. You see a lot of effect of ice dynamics. So there is some post-surge thickening in some of the basins. So there is an incredible amount of information in this image. So that was really nice to see. And one of the advantages of CryoSat is somehow the combination of relatively high spatial resolution with also a relatively high temporal resolution, where you can get, due to the monthly cycle, you can get interesting seasonal patterns and the change of elevation during the accumulation and melt season. You can also separate the trend in elevation basin by basin, or you can look at accumulation versus ablation area. So this is what Luca did here, where you can see relatively stable accumulation area some anomalously high accumulation in the year 2015, which you can see in there as well, and strengthening in the ablation area. So an incredible amount of information that you can gather at this scale. We went to Patagonia then afterwards, a slightly more challenging topography, especially in the southern Patagonia ice field. Again, that was the second area that Luca looked at. And Patagonia has, so ESRIN is mostly driven by surface mass balance, so the change are relatively homogeneous spatially. Patagonia has a lot of effect of dynamics, so you have glaciers which are thinning very strongly next to basins which are thinning less. You even have some of the basins that are showing dynamic slowdown and so thickening at the margin of the glaciers. And again, we can get these beautiful detailed pictures of the different processes or at least behavior of these different basins that are linked with processes related to surface mass balance or what's happening as well, or the relationship between dynamic and fjord processes. So you have detailed thinning pattern, and again, for each of these basins, you can look at how they behave through time, seasonally, but also on the long term. So that was a nice outcome of these studies. And we can see for Patagonia, there are if you disregard those two studies, there is a general increase in the loss of ice for Patagonia over that long time period. So then what Paul did afterwards during his PhD is to do an overall study of the glacier change in Arctic. So we have this pan-Arctic view of glacier change across Canada, Iceland, Svalbard, and the Russian Arctic, with again an incredible amount of detail, highlighting the role of surface mass balance and the role of dynamic. We get a very, very high coverage over these regions, and we can generate a mass balance estimate for each of the sectors. And that's basically adding a new tool set to the various satellite missions that are able to do this with these specific characteristics. And one very exciting, I guess, when we spent quite a lot of years doing R&D for this, and we are slowly moving to being able to do quite exciting new science with it. And this is, I think, one of my highlights, I would say. So we've heard a lot for ice sheet about partitioning between loss of ice or loss of mass due to surface mass balance processes and due to dynamic loss. So we've seen that in Antarctica, it's mostly dynamic loss. We've seen that in Greenland as well. And this is thanks to quite performant climate model, quite a good data set of ice velocities and ice thickness. But those things really don't exist for glacier at the global scale. And so we still don't really know what is the contribution of the atmosphere and what is the contribution of dynamic. And I think this is the first time that we are able to do this. So we exploit the fact that we have, again, splendid spatial coverage, and the fact that if you look at the SMB forcing on land terminating sectors of these glaciers, the change is relatively simple in some ways. It's really related to elevations. We have for the northern Canadian Arctic and land terminating, you have the change in elevation versus elevation, and you can see that, you know, roughly as you go down in elevation, you have high loss of ice, and if you are looking at high elevation, this is quite low. And the relationship between the two is quite striking and simple. There is also some effect of where you are. So there is latitudinal and longitudinal impact as well. So you can, from the observation of a land terminating sector, you can build a parameterization of the SMB. And what Paul did here is to compare that particular those observations. So you're taking observation of a land terminating sector, and you compare this to what regional climate model predict. And you can see that you have quite a good agreement between the two. So that's only observations of SMBs or this surface elevation change, thickness change. Now you can take the parameterization and you can predict what that SMB would be over marine terminating sector. Marine terminating sector can have both SMBs and dynamic change. And they are different from the land because they have a different altitude distribution. They also have a different location. And you can see that that parameterization does a very good job in projecting what the marine terminating sector SMB component would be. And so once you have that, you can basically partition over marine terminating sector what the losses, which is what's been done here. So on the left here, you have the imbalance due to surface processes. And on the right, you have the mass contribution from dynamic imbalance. Again, that's I think the first time we have this picture. And you can see that over the Russian Arctic and the Svalbard area, we have quite a strong dynamic imbalance. So overall, for this region in the Arctic, surface processes are responsible for about 80% of the loss. But over these particular sectors in Svalbard or Russian Arctic, the ratio is 1-to-1, or in some sectors, the dynamic imbalance dominates the total mass balance. And this is important when we think about projecting glacier loss in the future. I think the dynamic aspect is not yet fully there, and so it's not only SMB. Dynamic matters also for glaciers, particularly locally. Okay, so what about high mountain glacial regions? So we've seen sectors which have a lot of ice caps with relatively gentle, let's say, topography. But can we go global? Can we go for high mountain glaciers? And this is actually what we started with. So back in 2010, I had the YGT with ESA, and then Amory, who is looking good with his helicopter here, joined for a PhD in Strasbourg. And the first thing he started to look at was to ask the question, okay, where does CryoSat sample? And that comes down to the onboard tracker. So CryoSat has a closed loop tracking. It needs to, it has a range window of 240 meters, and it needs to know where to place that window to start measuring. And that's the process of onboard tracker. And it sends basically a pulse, and based on the response, it decides to place the range window at a particular elevation or range distance. When you look at regions like the Himalaya or Gulf of Alaska or high mountain regions, the range window and even the tracking window, which is 480 meters, is much smaller than the range of elevation within a footprint. And so sometimes you get a glacier at the range of the range window, and sometimes you don't. Sometimes you get the top of the mountain. The other aspect of onboard tracking is also that the tracking is applied at the next cycle. So you're also getting the range of elevation that corresponds to a few hundred meters before. So that's a challenge, obviously, and you'll get the outcome of that is that you're getting a loss of data. So that's a region in Pamir. The blue colors are glacier outline from the RGI. And the light blue is where the range window doesn't intersect glacier, and the dark blue is where it intersects glacier. So you can see that you have in some location good coverage, in others you don't have any measurements there. And that tends to vary a bit as well from year to year. So we estimated that there was about 60% in the Himalaya of glacier that were intersected by the range window. So 40% of it basically didn't have any data to play with. So that was 2010 and so, and we kind of left it for a while until Livia came about. And we decided to give it another go. So we can't really use the same sort of approach as we've used for the other regions because we have reduced coverage from the close look onboard tracking, but also because teledoppler is limited over large loop. So we really have a much reduced coverage. So we had to apply a slightly different method, which was inspired from what Icesat or people with Icesat did in that same region, which is to expand in some ways or coarsen the resolution, integrate over larger distances, and somehow find ways to knock out the underlying topography to be able to compare change along large length scales. And that was actually quite amazing because from radar altimetry, we were able to follow quite a nice spatial pattern of glacial change. So it actually somehow works, which is amazing. So Livia has a poster today, poster 40. So if you can find your way through Brella, I suggest you go and talk to her, and if you want to know more about this. This is a very exciting outcome. Okay. I don't know how I'm doing this time, but I have a few slides about looking ahead. So I think all this work over the last decades have led to us being in the position to be able to produce a global glacier assessment from radar altimetry, and that's exciting. I think if you compare the glacier community position with the one from the ice sheet, we are a bit behind. In terms of these assessments, I think it's probably harder to do, I would say. But we have now quite a lot of different methods and sensors and way to get to this. Grace has done quite a lot of studies on this. Icesat has been there. Now we have radar altimetry, DM differencing. And so we can start as a community to build more reliable global assessments. So that's really exciting, and that's coming ahead. There's a lot of activity within the RACMAC community to try to get this estimates a bit of the variability of this estimate a bit down. So this is from Livia's paper in Himalaya and the Gulf of Alaska, and you can see that you have quite a bit of scatter. A lot of it comes from the fact that there are different time periods, different definitions of areas and things, but we need as a community to come up with a standard framework to do this and try to have a better handle of what the numbers are. Operational projects. So the CryoTempo project we have mentioned a few times, EOLIS, that's providing
1 minute warning.
Say that again? 1
minute warning. You're doing great.
Oh gosh, that's a bit short. Are you sure your clock is not drifting? Or? Operational projects. So CryoTempo EOLIS, we have the ice sheet in there, and the glaciers are coming at the end of the year or early next year. Okay, Crystal. So that's a mission with the primary objective to look at glacier, so global glacier monitoring, and that's fantastic. And I think we've shown that that's definitely possible and doable, achievable, realistic. So if CryoSat was dreaming about Crystal, it would dream about a few things. So SWAS is an operational product and mode, and I think that's a plan, so that's great. Combining fully focused and SWAS, that's bold, but why not over these regions? And if you want to know more about this, you can go and see Albert's poster. Again, I think it's tomorrow, Thursday. So that would be an amazing achievement, increasing the spatial resolution and in both azimuth and across track. We need an onboard tracker, dedicated, intelligent, flexible, open loop onboard tracker. And I don't hear enough of it. I would have to say I don't read enough of it. So I would suggest we really think about that one and make sure that it works, because that would be a lot more data in those regions. I think 40% drop is if we can gain 40%, that would improve things dramatically. So we need to get that right. SWAS has extra calibration tool for attitude control, in particular roll. So there are a few papers there. If you're interested, Lawrence had something. We had a few figures in ESA, and then there is kind of a joint paper with Albert and Michele in RSIS, showing that over land sector, looking at the difference between ascending and descending, you can actually calibrate the role of CryoSat. And so that opens some possibilities as well for doing this as an operational method to improve that calibration, because for SWAS, that role aspect is very important. And actually, so from the get-go, CryoSat was really good at making, well, it was really nicely tuned for SWAS processing. We had really nothing specifically to do in the early days. The only thing that happened a few years ago was to improve that role calibration. And so that made things much, much better for SWAS. And so we can do that also for Crystal. And then we need to also improve our way to do phase to angle of arrival conversion, especially because CryoSat is nadir, but not quite. It kind of tilts a bit, which is great actually, because you can look at change over a very flat surface from SWAS. And so iceshelves, sea ice, and others, that's possible. We just need to get that phase departure aspect sorted. So there is a poster by ISIS and Alejandro and myself also later today. So if you want to discuss this, please go and see that. And okay, happy birthday, CryoSat. 10 years is great. Thank you very much.
Fantastic. Thanks so much, Noel, showing your proficiency with paint shop animation or graphics here in the last slide, as well as swath mode processing of CryoSat data. So brilliant talk. We've got a few questions, and we'll just take a bit of time to ask you those. So there's one from Andy Shepherd saying, I'm interested to know if there's a systematic nature to the areas not surveyed by the technique in mountainous regions. Do you know if this is the case, and if so, whether it is an important limitation, and could there be anything done to address this in future mission design?
I need to read because I think you spoke quite fast.
I did. You know me, Noel.
Let me see, where is the chat? So which one is it?
It's just if there's a systematic nature to the areas not surveyed by swath mode in mountain glacier regions, and if you could adapt to future mission to avoid this problem.
Yeah, so higher slope. So I think what we saw in some of the sectors is that there was a systematic drop of data over higher slopes, and I think that's down to the Doppler processing. So if we can improve that a bit, that would be good, I think. In terms of systematic change, that would be the one. I think we need to also investigate the impact of that tilt on crystal, because we can do a lot with that tilt with CryoSat. If it's perfectly nadir on crystal, I think we need to investigate what the impact of that would be, because that matters as well.
So Paolo has confirmed that open loop over the ice margin in glaciers is the plan for crystal, and Mark Junkwaters followed this up with a question saying that open loop requires DEM updates in dynamic glaciarized regions. Is this a serious issue or not?
We need to come up with a plan. I think it's not necessarily an issue. We need to think about how we do this properly, and how we can maybe use the measurement themselves to do an update as we go. I think we need to do scenario planning there. Yeah.
So that's a great suggestion. I think almost a recommendation that we could simulate the effects of this maybe in a pilot study before Crystal's launched, to try and investigate how serious an issue it would be, maybe, and how frequently the DEMs would need to be updated.
Yeah, I think in general, open loop, we need to work on the open loop and really spend some time with this. I know that there are some effort done in the frame of Sentinel-6, but I think we need to do more. Yeah. And that's definitely within. I think the MAG should promote that. Yeah.
So one final question from me was, in your time series, was a particularly low mass loss year for glaciers globally. It was almost zero or close to that. Why was that? And was it dominated by maybe an exceptional mass gain in a certain region? Have you any thoughts on that?
2018, you say?
2019, yeah, it was seemed to be particularly.
I think it was 2018.
Oh, okay.
So yeah, I mean, so that comes quite a lot from glaciers in Greenland and Antarctica, especially.
So snowfall gains in those regions, you think, or just?
Yeah, I mean, similar to the absence of mass loss in Greenland over that time period, which we saw as well from the talk by Simon yesterday. Yeah.
Fantastic. Right. Well, I think that's everything from now. Thanks for doing such a great presentation and for speaking in this session. I think we'll move on to the next talk now, which is going to be given by Jean Tonard. He's giving a keynote presentation on the contribution of 3 modes of CryoSat to iceberg studies, which is fantastic. So Jean, we can see you, but there's a lot of noise on your microphone, and we can't hear you speak. I don't know if you could mute and unmute and see if that makes a difference. We still can't hear you speaking. We can just hear white noise on your microphone, unfortunately. Matteo, I don't know if you're able to provide any technical support to Jean. So the white noise is still there even after you've muted and unmuted. I wonder if it could be worth reconnecting, as Tommaso is suggesting, or if you've got any microphones plugged in, if you could unplug them. There's lots of white noise. We can only hear awful white noise. Matteo, have you got a suggestion at all?
Yes. Can you hear me, Jean? You can hear me. If you have a headset, maybe try using that.
So we've got some fantastic suggestions from people in the audience about how to solve audio problems. I think we're all quite experienced in encountering technical difficulties in virtual conferences now, aren't we, after a year of coronavirus? And Mark Drinkwater is suggesting that we've got liftoff now. So it does sound quite a lot like a rocket launch, white noise. Here we go. So I can see Jean with a headset that he's plugging in. Let's see if this does the trick. Jean, if you would like to try and unmute your microphone, I think you're still muted currently. I don't know if you can hear me. Matteo, do you think you could help Jean unmute his microphone maybe to see if the headset works?
Yes, I've sent him a request. Let's see if he's able to unmute himself.
So Jean, we can still see you, but we can't yet hear you, and it looks like your microphone is muted. So if you're able to unmute your microphone.
Hear me now?
Perfect, we can hear you, and there is no
Okay.
white noise anymore. So that's absolutely
Okay.
fantastic. It looks like the technology is working for us.
Yeah,
And the
I don't know
audience
why
is
sometimes
still here.
it does that, but I never understood why. So I'm going to share now.
Perfect.
Okay. Met up.
So I think Matteo should have given you the power to share your screen. It's the share button down at the bottom.
Yeah, it's okay. Up. Do you
Okay.
see the screen?
Yep, so we can see your desktop at the moment.
Okay, but now I have to. Can you still see?
We can see your desktop still.
Oh, okay. So it's not a good screen.
So we can see your slides now, but they're not in presentation mode yet.
Okay, that's good. That's okay. Perfect.
And you're away. Perfect. Thanks so much.
So sorry about that technical problem sometime. I'd rather be in Taormina in real world than that. I don't really like virtual presentation, but it's better than nothing. So this presentation, and I was so glad to see a young scientist working on icebergs and altimeter, but I will do a general presentation on this huge contribution that the three modes of CryoSat made for iceberg studies. So I like this image because it gives a good idea of what is an iceberg, can be an iceberg field. So it's a little bit old. It was the explosion, I think, in 2010 of the C19 iceberg, which was one of the largest ever in the Southern Pacific Ocean. So after 2 years in the Southern Pacific, traveling around pretty north, like 55 north, it really did explode. And the largest piece in the center is still about 20-40 kilometers long. But you have thousands of icebergs around, ranging from some 100 meters to some kilometers. And we see all the problem too here with SAR images because of the incidence angle and the different, in fact, backscatter as a function of incidence. In SAR images, it's extremely difficult to do an automatic detection of iceberg. But anyway, it shows that how important it is to detect icebergs and how complex it can be. So there was already some aspect of this that have been presented before on the scientific context, in fact, of iceberg studies. So we know that there is still a pressure in the Northern Hemisphere now for shipping. So not that I'm fully agree about using the northeast and northwest route, but there will be companies doing that for application. It's already done anyway. But mainly icebergs are also a key component of the ocean circulation at high latitude. They have a strong impact, in fact, or could have a strong impact on climate through freshwater flux and cooling and transport of also nutriment in the Southern Ocean. And as said before, they are about half of the mass loss of Antarctic ice cap, but and also a significant part of the Greenland ice cap loss too. And the difference between melting directly or the basal melting of ice shelves is that the iceberg can transfer, in fact, fresh water very, very far away from the coast into the ocean interior. Like in the southern Atlantic, they can go thousands of kilometers away from the continent. And what we know from previous studies that in the Southern Ocean, in fact, large icebergs, the ones that are above 100 square kilometers, transport the major part, in fact, of the volume of ice. But the small icebergs, in fact, do the freshwater flux through melting and wave erosion. It's extremely important to see that those very big icebergs, they don't melt very fast. So in fact, they are mainly disintegrated, not melting. And in fact, some years ago, we showed that altimeters are quite a powerful tool to detect and characterize small icebergs. That is, in fact, icebergs that are significantly smaller than the altimeter footprint. But they can also be used to analyze the elevation profile of large icebergs that are much larger than the footprint. In fact, the problem we have is still the intermediate ones, the ones that are too small to really present an elevation profile and too big to fit into the altimeter footprint. So they will change, in fact, the waveforms too significantly to be analyzed. And since 2012, so we maintain a database of small icebergs with detection, probability of presence, area, volume of ice, and mainly from the analysis of LOM waveforms. And we have a continuous now series from 1992 to 2020, and we have 14 altimeters. And we have also, because it's much more work, as already shown just 2 talks before, it's more difficult for large icebergs, but we have a 10 years database, in fact, from 2002 to 2012 for all the large icebergs of the BYU and NIC database. You know, we use the tracks and we have the elevation profile, freeboard profile, in fact, for all these icebergs, all the ones that were available. It's more than 6,000 profiles. But what is important with CryoSat is that for the first time, we have 3 modes of operation on the same altimeter. So we have the classical LRM used since CSAT, but we have also the delayed Doppler altimetry, near and over sea ice, and the interferometric mode, which at the same time delayed Doppler and interferometry. And these 3 modes, in fact, can be used for both the analysis and study of small and large icebergs. So just to come back, it's for people who don't know, I presented this slide very often, but still, I love the principle because altimeters were absolutely not designed for that. But in fact, we noticed with 3, in fact, lighthouses in the Strait of Malacca, so far away from the Southern Ocean, but that there was parabolas in the waveforms looking at them. And in fact, when you do the computation, is that any small target that is emerging from the sea surface and which is bright enough in microwave, can have a detectable signature, in fact, in the thermal parts that is before the sea surface, in the waveforms. And this, if we look at the waveform continuous one after one, as long as the satellite progresses along its orbit, the signature of something emerging from the sea is exactly like a transporter response. So we have a parabola. And parabola shapes are really easy to detect, you know, as long as they are coming out well enough of the noise. So we use a classical detection algorithm based on convolution between the waveform and the parabolic filter, which represents the theoretical signature. this theoretical signature depends only, in fact, on the orbit parameter of the satellite. And after we have the position and the range, which is in fact the telemetry sample where it's detected, and the backscatter of the target. And we have two parameters that depend, in fact, of four unknowns: the distance from nadir, the surface of the iceberg, the elevation, and the iceberg surface backscatter, the ice itself. And we have two parameters and four unknowns. So using an analytical model of waveform, we define a model that can be used to relate, in fact, the range and backscatter to the surface, the area of the iceberg, assuming a constant freeboard and a constant ice backscatter. It's quite crude, but it's always the same. So we can study the variability, in fact, of the iceberg's volume of ice. So just to show that the method is working, is that if you study the whole globe, you also detect all the ships. We are also following, in fact, the ship traffic. For the first time, we did the analysis of 2020, so the ship traffic went down by more than 10% in all, in fact, ocean basin, which is the first time, even in 2008, 2009, there was no real decrease, in fact. So if we look at LRM mode, so here, sorry, I found the very nice figure I found is for ENVISAT, but it's exactly the same for CryoSat. So if we have a large iceberg, then we can collocate, in fact, here precisely with a Landsat image, MODIS image, and we see the profile and the waveform. So the ice range is not always working very well, at least on the edge of the iceberg. So we define a new, very simple, in fact, because the gradient is, and we are not, looking for a precision of centimeter, but 30 centimeter alpha bin is okay. And so we can very easily, in fact, estimate the freeboard. So here, the method is not taking, it's really the freeboard versus the sea surface. So that allows to get rid of all the problem of geoid and so on. We are really looking at the freeboard, not the ocean range or ice range. So this is an example, pretty much like what you see before. We were using that for the E68 iceberg. So we were tracking the iceberg using Sentinel-1 A and B images. So this is the example of, I think it's almost 6 months here of displacement of this iceberg. So as the shape is not changing very much, we track, in fact, the centroid of the iceberg, and we have the orientation. So we have a moving frame of reference, and we can, in fact, remap all the altimeter data available within this moving frame of reference. So for this particular case here, it's several months, but we use LTK and Sentinel-3 A, HY2A, and CryoSat-ESRIN, but here it's pretty much a long track. It's not swath processing. And we can, in fact, use all this data to intercalibrate. And we can, by objective analysis here, a simple method, and we can compute the altimeter topography. And this is a comparison between the altimeter topography, including all the available altimeter data, and a comparison with RIMA, the reference elevation model of Antarctica. And it's pretty good. And we see some difference in the south here. And in fact, we noticed that we computed also the altimeter topography before, in fact, the breaking, because we have all the data, and we noticed that there was a slight wobble. In fact, the constraints were released, and there was a change of elevation in the south of the icebergs. So if we proceed now to the SAR mode, so in fact, for the CryoSat LRM mode, it's pretty, we use it exactly, in fact, like all the other altimeter. But now, so CryoSat was the first altimeter to use, in fact, the delay Doppler processing. And the delay Doppler mode processing, so include, in fact, range element, including slant, tracker, and Doppler range correction, and also stacking and incoherent summation of stacks. of collocated Doppler beams. So in fact, if we consider this is exactly the same, in fact, using the same raw data level N1, we can compute also pseudo-LRM and SAR processing. So in pseudo-LRM, we will have this nice parabola, but in fact, the slant range correction and the stacking, in fact, transform the parabolic signature into a simple position because the iceberg is not moving, so the stacking is supposed to put back everything together. And so we reduce, in fact, the parabola to a bright spot. And also, we can see that the stacking will really reduce the noise level in the thermal part, in fact, of the waveform. But bright spots are really easy, in fact, to detect. And there are a bunch of image processing algorithms used most of the time for medical application, but so it's very, very standard. What we can see also is this example is that we have a very bright parabola into LRM, but we have also some slight echoes. And if we look at the SAR processing, we will have, in fact, this bright spot, but several bright spots that might correspond, in fact, to different level of the iceberg or different position or edge, of the icebergs. So this is another example that we use in the paper, but just to go along, we were sure that there were two icebergs near Greenland here. And in pseudo-LRM, we have the nice parabola, and we have the detection using pseudo-LRM and convolution product. And here we have detection using SAR data. But what is interesting is that if we look at the DDM here at the maximum, we clearly see here the nice iceberg and different echo. And with stacking, we add a little bit of noise because the position is moving, or there is also slight error in the processing. But we see the different also level of the altimeter. And every time we have to study a little bit. But for ships also it's true. It's not horizontal. There is always a slight Doppler shift, but that might correspond, in fact, to different position on the icebergs. So SAR is very nice. The detection is very good. We detect several levels, different echoes. We detect much smaller echoes also because the noise level is lower in the thermal part and the signal-to-noise ratio is much higher. But still, we have no direct estimate of the surface, the area of the iceberg, and we have to go back to the same method as pseudo-LRM, in fact, to compute, to estimate the area of the icebergs. But just to go back fast, because SAR mode now is very classical. Sentinel-3 has SAR mode, and I think it will be the basis for altimetry now. So the delay Doppler processing, so we improved, in fact, the signal-to-noise ratio and the noise of the thermal part. We have a much simpler iceberg signature, which is bright spot, and they are easily to detect, especially when you have a reduced background noise. And the higher SNR, in fact, reduces the false alarm rate. That happens sometimes with LRM. But still, we have this multiple bright spot at the same location, and it's not always easy to analyze. It might be also, we have cases when we know it's several icebergs very close together, or is it different portion of the same iceberg? So it's not possible, in fact, to discriminate between these cases. And the iceberg surface also can only be estimated through the same way as LRM. But this is now standard, and for Sentinel-3, we process both PLRM and SAR data, so we can have direct comparison. And the results are very similar in terms of volume of ice. Even if SAR detect much smaller iceberg, we can detect something less than 50-meter size, but they don't carry a lot of volume of ice. So if we go to the best mode now of CryoSat, it's ESA-ESRIN. It's fantastic. It's incredible for what the quantity of information that are in the ESA-ESRIN mode. So the principle is very has been widely described. So, but just we have two antennas, so the difference of range between the two antenna and the target on the surface lead to a phase difference. So what is important to notice is that for small icebergs, we don't have to care about phase unwrapping because we are not far away and we are not big enough and high enough to be more than 2 pi, sorry. And what is important is that because of the interferometry allows us to discriminate, to give the distance from nadir. And also which side, because of the phase sign, which side of the antenna of the satellite track you are. And from the range and the distance from nadir, from the phase difference, we can estimate, in fact, the elevation of the surface of the iceberg in this case. But what is important too is that when you look at the coherence, normally in the thermal part of the waveform, it's purely noise. But if you have a physical material surface in that, like an iceberg, it becomes very coherent. So you have a coherence which is close to 1. And this can very simplify, in fact, the detection, because you have both the bright spot and you can ensure that there is a coherence high enough to be sure that you have something. So if we look at the theory, you know, everything in interferometry can be explained by simple geometry. You have a relationship between distance from nadir, off nadir angle, and phase difference. And most of the time it's parabolic shape as a function of distance. Here, in fact, I put it as a bin number of the waveform. But we should have this parabolic shape so we can invert, in fact, from phase difference to off nadir angle and off nadir angle to distance from nadir. But in fact, there were work by Reicha in 2017, and it shows that when you have, in fact, complex, the signal is not laser, it's a little bit more complex. So when you do the cross-product impulse response, the theoretical one, and if you include a roll or pitch angle, they start to have a wobbling, in fact, especially near nadir, and you don't follow, in fact, pure geometry. And thanks to Michele Scagliola, he provided us a model, so we have a matrix, in fact, a tabular form of the correction as a function of roll angle and for the interferometric mode. So we can also very easily control that. So we have a certain number of passes over the ocean. And so here it's over the Agulhas current. So normally we have nothing in the waveform. So it's very nice ocean waveform. If we look at the coherence, we have the one coherence at nadir. And after we start to have the and we start to have the coherence going down very close to nadir, and after we have the classical decrease of coherence, but still it's very high here as a function of nadir angle. If we look at phase, here we unwrapped it, but it's very simple because it's so flat. We can look, in fact, at the mean the phase difference as a function, in fact, of the bin number. Sorry, and we see that the wobbling is pretty much there too when we unwrap here, and it's very close, in fact, to the numerical model of Reicha for the off nadir angle we given in the data. What is interesting to notice too is that, in fact, if you look at the distribution of the phase difference in the noise part of the waveform, it's a Gaussian, and in fact it's centered at the different phase difference corresponding to the off nadir angle. So it's a good test also to control, in fact, the off nadir angle estimate. But using that, we can correct, in fact, the phase difference that is measured. So this is an example here also with five icebergs detected off the coast of Greenland. And in fact, you have the waveform and...
One minute time warning. Just 1 minute time warning.
Yeah. It's pretty much finished, yeah. So we have the bright spot corresponding to the icebergs. We see that they are very coherent, they are almost one, so it's very easy to detect. So we can see also the phase difference over these icebergs, which is also very homogeneous. And we can compute, in fact, the freeboard and the distance from nadir. So this is an example here to better show, in fact, what does change to correct or not the phase difference. So this is I isolated one iceberg because it's easier. So we have a very nice bright spot. It's very coherent, coherence above 0.9, and the phase difference here is around 2. And if we look, in fact, it's in open ocean, so we can look at the mean phase difference over the ocean, and we have this nice wobble also corresponding to a roll of 0.5, and there is a very good agreement between the mean phase difference and the model. So we can compute the freeboard here using the raw phase difference, and we have this kind of result. But if we modify, this is pretty much the one using the mean or the geometry. They are very similar results. But it does change, in fact, the position of the iceberg and the elevation too. So in fact, we have a program that uses, in fact, the model phase difference to compute the iceberg area, freeboard, and position. So we here, just an example, we can now compute a lot of, detect a lot of icebergs and analyze their freeboard and area. And here it's a distribution of freeboard around Antarctica. And we have to do more detailed study now because we have thousands and thousands of signature. The problem is that they are very, very close to the coast. So we don't have the full, we can't really see the melting, for example. So what is important is that we can also use the source processing to study large icebergs. So this is an example over A68. So in fact, we correct the phase using the theoretical model, using the roll angle. And this is inverted. This is the topography from the phase difference and the source processing. And this is the REMA model. So it's an 8-meter design computed using stereo photography. And this is the inverted backscatter. It's extremely, there are still some effect of roll angles that are not completely corrected, but it's fantastic. This is 50 meter across track, 300 meter along track resolution. And we see that we have a very, we can see the pressure deep, we can see a lot of feature on that. And sometimes we can even see that the REMA topography is not good. For example, we have this deep here and crack. And in fact, when they did process the REMA, the stereo pairs, the iceberg has been moving, so there is this duplicate and this mirroring here that is not right, you know, and the CryoSat processing shows that. And what is really exciting now is that we can also compare with Icesat. So this is also a remapping of Icesat on over the A68 topography, where we really see, in fact, all the ridge, and we can compare with either other satellite altimeter or CryoSat SAR processing. So just to conclude, so the 3 modes can be used for both small and large icebergs. But just to make it short, the interferometry is so promising, and there are so much information that we can still learn from that. And it has to be corrected, it's true, for roll and pitch effect. But the advantage of having a slight roll is that the echo will come mainly from always the same side. And it's much easier to process something that is coming of the same side of the altimeter than having stuff that go from one side to the other. Because icebergs are quite flat, in fact. So it's much better if we can have everything on the same side. So thank you for your attention.
Fantastic. Thanks so much for that brilliant presentation. Okay. Jean, you coped wonderfully with the technical glitch right at the start. I don't think any of us remember that now. So great to see your results. if you'd like to stop sharing your screen, we can still
yeah.
see your desktop at the moment.
Okay, that's good.
And we've got.
Is it good? No, it's not
No,
sharing anymore.
we can still see your desktop, but there's nothing dangerous up there, so don't worry too much.
I can't. How do you shut down? Because up.
If you see the little orange section at the top of the screen in the center, if you click that, you just stop sharing.
Ah, okay. Yeah.
Are there any questions for Dean? I can't see any in the chat at the moment.
Okay, so let's stop sharing.
Yes, stop sharing now. Yes, you're safe. Have we got any questions from the audience at all for Jean? I appreciate we're running into our lunch break now, so if Jean, I'll ask one final question before we wrap up, because I don't see any from anyone in the audience. Now that you've got this fantastic data set of icebergs, are you planning to sort of investigate whether there's been changes in iceberg behaviour, where they're moving, or how quickly they're disintegrating over time? Big picture question.
Yeah, so in fact, it's not only, putting together all the altimeter. We have this climatology, and since 3 years we see a real increase of icebergs, volume of ice in the Bellinghausen and the Amundsen Sea, and it's certainly related to the Pine Island and Threat. So with 1 or 2 years delay, we see all the plumes of iceberg going all over. What we see too, going back to large icebergs, is that it's a lot of work. I said before, studying large iceberg is really time consuming, because we have to find sentinel data, we have to remap everything, because they are turning quite fast, so we have to remap. But we can really analyze the melting and fragmentation of large icebergs, and we can also see the huge plumes. It's true that if you look in Antarctica, you cannot explain in model, you will never be able to explain the freshwater flux with iceberg without putting at the same time large icebergs and small icebergs. And you have to be able in your model to disintegrate large iceberg, and it's extremely difficult. But the plumes, we find icebergs in the Southern Ocean up to 45 south. So that's very far away from the continent.
Well, it's a fantastic resource and a great data set for investigating iceberg behaviour. So I look forward to seeing future presentations on that from you. So thanks once again for your talk. Just to remind everyone that there is a poster session associated with this conference session later today. I believe that it is going online or starting at 17:40. So make sure to visit the poster session associated with this session. There's lots of great science going to be presented there. And with that, can I hand over to Lawrence to give up the summing up remarks from the session before we go to lunch?
Okay. Thank you, Anna. Yes, I'd really like to thank all the speakers this morning. It was worthwhile for me to get up at 3 o'clock in the morning. And I think it was an excellent session with varied speakers and varied topics. So again, have a good lunch, breakfast, or whatever time it is in your time zone. So thank you very much.